Thank you very much. It's a pleasure to be here tonight. Thank you, everybody, to come on a Friday night. Hopefully, we're going to be able to see some stars later. And today, I'm going to talk about the most massive stars. Well, not exactly all of the most massive stars, but especially the magnetic massive stars, which are my favorite star ever in the world. But before, I thought I would tell you a little bit about me. So as Dr. Batcheldor said, I'm from Canada. See, so this is what I usually look like, especially in the winter. And I was basically trained, or I started astronomy as an observational astronomer. So this is where I used to spend a little bit of time observing the stars. It was a bit chilly, slightly. But then at some point I moved to a slightly bigger telescope in a bit more picturesque location. Still a bit of snow on the summit of Mauna Kea, Hawaii, about that big. But you know, you drive 2 hours away and this is what's at the end of the road, which is always quite nice. So I'm quite delighted now to be here at Florida Tech, and that was my reaction. Yes, there are palm trees that I can see from my Windows office. So it's really a pleasure to be here and study stars. But I guess the questions that you might be asking yourself at this point is, what are stars, really? Okay. So when we look at stars, this is sometimes what we're going to see when we look at the sky, especially in region like here in Melbourne when we have a lot of lights outside. And you might be recognizing the constellation of the Big Dipper. I always have to think, because in French it kind of pronounced it a bit like diaper. So I said that in class 1, the constellation of the Big Diapers. They laughed at me a little bit. But if you go to places that are a bit darker, you're going to see that there's actually a lot of stars. Right? And if you go places that are even darker than that, like for example, if you were to stare out of the window of the space station, this is a real picture, you would see a lot of stars. So right now you're seeing the Milky Way, our own galaxy, all the stars in our own galaxy. But if you think about our sun, you might have heard that our sun is actually a star too. Right? It's big, it's round, it's bright. How come the stars, they don't quite look at that for real when we look at them in the sky? It is actually just a question of distances. So think about when you're outside and there's like a car right in front of you while you're walking or running around at night, and you know it looks very, very bright. But if you think about cars that you see at the end of the road a couple blocks away, 10 blocks away, they're pretty dim. Right? So it's just a question of distances, that the stars, the other stars in the sky, are just very, very far away. How far away, really, are they? So you might have seen that picture before. So this is a representation to scale of the element in our solar system. So you can see the sun and the planets. So the size are to scales. But the distance in there are not, because we had to squish them all together so we can see them all. So how far away are things in our solar system? So I couldn't find any tennis ball. I don't know in which box they got moved down to Florida. So here's our sun, okay, the size of an apple. Look at that. This is a little peppercorn. This is about the size of the Earth, if this is the size of our sun. It's pretty small. How far do I need to put it to be at the right distance? 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12. So this is about the distance I will need to put the peppercorn to represent the Earth. So I have another apple. This is the closest star to our own sun. How far do you think I need to put it on this scale? Okay, the Earth, wave the Earth. The Earth is over there. How far do I need to put this apple? Well, first of all, I would need to drive all the way to Orlando so that I could board a plane and go put that star all the way to Chicago. Okay? It takes 8 minutes for the light from our sun to reach the Earth. It would take 4 years, 4.2 years, for light from our sun to reach the closest other star. So we're talking about very, very big distances. And that's why I'm not going to go and put it all the way in Chicago, because I'm not going to be back in time. So this is why the stars really don't quite look like our sun, because they're just too far away. Okay? So are all the stars, are they all of them exactly like our sun? Right? So we're quite lucky because we can look at our sun in great detail. We're really, really happy that we're really, lucky that the sun is so close. Well, also if the sun was not so close, it would get very, very cold around the Earth. So that's one thing that is very nice. But we can also study it in great details. And you can see right now, this is a picture from 2 days ago. I don't know if you heard, there's like a gigantic sunspot nowadays. Okay, so we can study this, the surface of our sun in great details. We can also have, video. Video. There you go. So nowadays, with instrumentation and telescopes, we can see the sun in so much detail. What you're looking at right now, our coronal loop, is actually a magnetic field that gets filled with hot gas and is evolving with time. And this is a teeny, teeny patch of the sun. Okay? We can even see it, so this is very cool. We can even see the sun from outside of the Earth. For example, there's the 2 satellites, which are called stereo, which are not in orbit around the Earth, but are actually in orbit around the sun, each at opposite place. So we can actually see our sun from the front and the back at the same time. Right? This is pretty cool. So our sun, we can study it in great, great details. But when we look at stars, all we see are little dots of lights. But you can already tell, let's look at this for a second. Are they all do they look all the same? No, right? Look at this one, that big one over there on the upper left, which is Betelgeuse. It's really orange, is it not? And if we look at the bottom right over there, this is the constellation of Orion, by the way. This is Rigel, and Rigel is very blue. So we can see that stars actually have different colors. Interesting. So if you had this, if you see this, that stovetop element, would you put your hand on it? No. Why? Because it's hot. It's really hot. So we already know intuitively that hot things glow. Okay? But I'm kind of warm, especially in this weather, right? How come, am I glowing? Yes? Dr. Batcheldor. Am I glowing in? Yes. Can you see me actually glow? What would you need to see me glow? Infrared, right? So I'm actually glowing. I'm just not glowing in a wavelength that my eyes are able to see, because I'm not as hot as a stovetop. How is it called in English? Stovetop element, whatever. Right? So I'm actually glowing for real, but in infrared wavelength. And it's because there's a relationship between the temperature of an object and the wavelength, the color at which it emits most of its light. Right? So if you have something that is very, very hot, it's going to be bluer. And if you have something that is colder, it's going to be redder. Right? Remember when we see, for example, this is, what's the word in English for that? Metal worker, blacksmith, right? Blacksmith. So imagine that a blacksmith would heat iron, right, before smashing it into the shape of a leaf right now. So which part is the hottest, you think? The leaf or the rod? Which one is the hottest? Yeah. So the leaf is very red, and the rod is more white, right? So you can imagine that if it was peaking in the green, you mix all the color together, it will look very white. And if you start to heat it up even more, what is usually, so you might have heard that before when you look at a flame, which part is the hottest part of the flame? The blue part, right? But that's not all. If you look at the leaf and the rod, which one is glowing brighter? The rod, right? So the white part is actually glowing much brighter. So there's also a relationship between the luminosity, which is how bright it's shining, and the temperature. So objects that are hotter are bluer in color, and they also shine more fiercely. Okay? But then that's not the end, quite the end of the story. So if you look at a candle versus a big bonfire, which one is the brightest? Which one is going to be more luminous? The little candle or the big bonfire? The big bonfire, right? So the luminosity of an object is going to be dependent on its temperature. So the hottest it is, the more bright it's going to be. And also the biggest it is, the more bright it's going to be. And this is something that we can apply, that we know that we can apply to stars. And I'm going to show this video because I think it's very awesome. So this is from the Space Telescope, Hubble Space Telescope team that explains. There you go. You don't need to read that. I'm just going to go. I think it is very, very well done. It is really cool. I like that movie a lot. It's available on the Hubble website. So basically, what that video shows is what we call an HR diagram, an Hertzsprung-Russell diagram in which we like to classify the stars. It's like a family portrait. You know at school where they put you in order of height? But instead, the stars are ordered from the dim stars to the very bright luminous stars, and from the hot stars on the left side to the very cold star on the right side. Most of the stars are going to spend they're going to spend most of their life on that diagonal region, which we call the main sequence. Okay, the stars are born there, and until they die, they're going to stay at the same place. And then when they die, they're going to become supergiant, and they're going to go in different area of the diagram. But most of the time, they're going to be in that main sequence. Okay, this is what the things we find on the internet. And that was very, very funny. Anyhow. So not only the stars are ordered by luminosity and temperature, but it also turns out that on that main sequence, they're also in order of mass. Right? From the low mass star, which are red and dim and small, to the most massive stars, which are big, hot, and bright. So the stars are actually a bit different. But where do the magnetic field comes in that whole story? Do stars have magnetic fields anyway? Yes, they do. And one of the good examples is actually our sun. So our sun is in the middle, roughly in the middle of the main sequence. Not too hot, not too cold, not too bright, not too dim. Right? We're kind of a Goldilocks star. And our star has a magnetic field. And in fact, we find the strongest magnetic field inside of the sunspots in very small region, where the magnetic field strength reach 3,000 Gauss. So a Gauss is a unit of magnetic field strength. And to give you an example, the magnetic field of the Earth is about half a Gauss. Okay, how does that relate to things we know? Right, so I can give you a little example. So in our brain is actually a magnetic field in there, which is about a nanogauss, which is very, very small. Magnetic field of the Earth is half a Gauss. The magnetic field of the Sun outside of the sunspot is about 1 Gauss. Fridge magnets, 30 Gauss. Okay, sunspot about 3,000 Gauss. An MRI machine is about 30,000 Gauss. The biggest man-produced magnetic field, and it's quite funny that there's 2 categories for the ones that have been produced with and without the lab actually staying intact. Okay, it's about 20 megagauss. And neutron stars, which are cadaver of massive stars, are actually the most magnetic object known in the universe. So if we look at our sun, you can see here, so this is a movie from the last 2 days, okay, where you can see the big sunspot, and on the right side is what we call a magnetogram. So everything that is gray is weak magnetic field, and everything that's bright white or dark black is actually strong magnetic field. And you can see that the magnetic field corresponds to the location of the sunspot, and that one is huge. It's very, very big. If you look at the sun with these eclipse glasses, like we were doing last night to see the eclipse, you can actually see the sunspot with your naked eye, protected naked eye. Well, the question is now, you might ask yourself, how do we measure magnetic field anyway? It's not like you can take an instrument or a compass and go all the way and put it on the sun. It's probably going to melt, probably going to die. So how do we do that anyway? We do that with light. Okay. Some of you might have seen in your high school physics that light is actually a wave. Okay. Light is an electromagnetic wave, and the period of its oscillation is going to correspond to what we call wavelength, which is what we perceive as color. Okay? So for example, if you have a beam of light, it can be separated in its different wavelengths by a prism, which will create what we would call a rainbow or a spectrum. Okay? So red light has a longer wavelength, longer oscillation than blue light. For example, this is the spectrum of our sun. Okay, so you can see, is that thing going to work? Here. The spectrum of our sun. Okay, and the bottom is just a graphical representation of the information that you see in the color pictures, where you have the brightness as a function of wavelength. Okay? And you will notice that there are some little black stripes. Can you see that? It looks like there's some light missing at some very specific wavelengths. That is because while the light is going through the atmosphere of the sun, okay, there's something that can happen to that light because of the atoms. So atoms, you can think of it as a nucleus made out of proton, and the electrons are whipping around. Okay? But the electron cannot be anywhere they want. They have to be at certain places, or at certain physical terms, have certain energy levels. It's a bit like a step ladder. Okay? And they can absorb and steal a photon only if that photon has the right wavelength, the right energy, so that the photons can go up the ladders. Okay? This is what's going to create these little black stripes, which we call spectral lines. And it turns out that when you have light that goes through a medium that has a magnetic field in it, these energy levels start to have a little bit of a multiple personality problem. Okay? So the energy level are going to split into different little sub-level of different energy. It's like you have a step ladder and you add little steps in it. And this is called the Zeeman Effect. So instead of having one spectral transition between two energy levels, one spectral line, when you have a magnetic field, you're going to have more than one. So with light only, we can actually measure magnetic fields. So this is an example. This is a zoom of a sunspot. Okay? And on the right side, this is a spectrum. So if you look at the sun, at the spectrum, at a place where you're not in the sunspot, you will see these little spectral lines. There's 2 of them over there. But if you look carefully at the spectral lines when you're inside a sunspot, can you see them splitting into 3 components, right? So then that was the first application of Zeeman Effect, which was a physical, something that we knew in the lab, and it was the first application of the Zeeman Effect to an astronomical object. So Henley knew about Zeeman's work, and he says like, well, look at that, in the sun it happened. So he guessed that it was because the magnetic field in the sunspot was much stronger than in the rest of the sun, and he was right. Okay, so that's why we can measure the magnetic field at the surface of our sun. But if you think about just stars, right, our sun, we can see the whole surface. We can measure the individual sunspot. What about a star that is very, very far? Are we going to be able to see anything? It's just a dot of light. But this is where we can get clever. Okay? We can use the fact that stars are rotating. Right? So imagine, sometimes, who have heard of the Doppler Effect before? Okay, a lot of people. Who have noticed that when you hear a car going very quick next to you, it does okay, let me try that again. Did you see that the pitch of the sound changed? Which means that the frequency of the sound wave changed. Okay, so this is what the Doppler effect is. And it's exactly the same for electromagnetic waves, waves of light. So something that is going towards you is going to be shifted to red color. Something that goes away from you is going to be shifted the other way around. Sorry. Something that goes towards you is going to be shifted to blue color, and something that is going away from you is going to be shifted to red colors. So imagine I'm a star and I'm rotating. What's happening to that side of the star?
Moving away.
Moving away. This one? Towards you, right? So you can actually see a side of the star going towards you. Blue shifted. Away from you, red shifted. And at line center, you don't have any velocity towards or away from you, so you're just going to have no shift in frequencies. So as the star rotates, we can actually look, so for this is an example where you have sunspots at the surface of the star, which are darker. And this would be one line profile that we look at very, very high resolution. And we can see the feature at the surface of the sun traveling through the line profile. And on the line side, the right side, what you see is the same effect for the polarization. The Zeeman effect also induced polarization that we can study. I'm not going to go in detail about this. So what we can do is sit at a telescope for a while, okay, and look at a star as it rotates around its axis and take a lot of measurements. Okay? And with this measurement, we can figure out, as things go in and out of view, we can figure out the structure of the magnetic field. Right? So with the telescope, to be able to resolve a feature about that size with just by making an image, we would need a telescope that would be about 100 meters across. Okay? And we would need to put it in space or get rid of all the atmosphere, which might not be quite practical. Okay, so this is what we call time-resolved spectroscopy, and it's a very, very powerful tool, which means that we can go by looking just at a point of light and take spectrum and get, okay, prepare for this a bit, and we can get the whole structure of the magnetic field of the star. Pretty cool, eh? So from that, we know that the magnetic field of all the stars that are like our sun or less massive than our sun have the same magnetic characteristic. They're all very complex. They have spots. The magnetic field is really located in these small sunspots. They're very dynamical. They have flares. They have magnetic activity. And this is because they're created by a dynamo mechanism. So you know when you take that flashlight that you just crank, there's a little magnet that turns inside of it to make electricity. It's the same type of mechanism, but instead you're moving the charge, which is the electricity, which creates a magnetic field. Okay, so we know that all these stars, like our sun, although are mass produce their own magnetic field as we speak by this mechanism. And this is because they all share the same internal structure. Okay? So stars, why do they shine? It's because they actually have nuclear fusion. They're producing energy in their core. And that energy is just moving outward, okay, and creating light. That's why they shine. But there's different ways you can actually transport energies. The photons, the light, can actually transport energy just by moving the light. Okay, they can carry energy. When you put you can feel it, right? When you go to the beach in the middle of the summer here, you can feel the energy of the light quite well. I burned. That was crazy. Okay, but there's also another way you can carry energy around, is to just take something that's very hot and physically move it upward and take the stuff that is cold and bring it down. It's like boiling water. Okay? So for stars like our sun, in the center of the star, the energy is carried away by the light, by the radiation, and in their outer envelope, it's carried away by these rolling motion. Okay, and I can actually see it. This is a picture of the surface of our sun. It's a little video. Okay, very, very zoomed in. And you can see what we call the granulation. So what you see is basically a consequence of of all that boiling motion on the surface of the sun. But for massive stars that are much more massive than our sun, the story is a little bit different. So what is special? What is special about massive stars, which I think are the coolest, well, the hottest star in the universe? Yeah. So we're talking about all the stars.
2030.
Thank you. You can add that to your list. Close your cell phone and to have the speaker closed. the time in there. Okay, so by massive stars, I'm talking about all the stars that are about 5 times to up to 60, 80, and 100 times the mass of our own sun. That's big. Okay? And what's pretty cool about these stars is that the more massive a star is, the shortest its lifetime is going to be. They're bigger, they should burn for longer. Right? Yeah. But it's because they're much, much more luminous. They're shining much more brightly, which means that they're creating energy at a much, much faster rate. So they're going to run out of fuel, basically, much quicker. Okay? And just to give you an example, let's say that we represent the age of the whole universe by 1 year. A star like our sun would live for 10 months. Not bad, right? It's nearly the age of the universe. But a star that is like 30 times the mass of our sun would live for only a few hours. That's short. Okay, they don't live for a very long time. Which means that if you see massive stars, they're young, and they didn't have time to go very far from where they were born. So massive stars are basically tracers of star formation. So this is a picture of 30 Doradus, which is one of the biggest stellar nursery in our local environment. So it's in the galaxy, the large Magellanic Cloud. And you can see all of these blue stars in that stellar nursery where other stars, less massive stars, are still actively forming. Okay. And the other thing that is very, very cool about massive stars, hot, whatever, is that these are the stars that will, in their core, create practically all of the heavy element in the universe. And by heavy, I'm even talking about carbon, oxygen, silicon, phosphorus, iron, everything. Okay, our sun is not going to be able to create a lot of these elements. They're all created in the massive stars because they are the ones that are going to be hot enough in their core to fuse all of these metals, which are rejected in their environment when they explode as supernova at the end of their lives. And because they live for a very short time, there's been zillions of generations of massive stars since the start of the universe. So they've been basically polluting, in a good way, the universe with the metals that are essential to make planets, life, everything. Okay, so when they say, you've heard that like a million times, I guess here, we are cosmic dust, but we're really just massive star cosmic dust. Okay. So what is different also between low mass stars and high mass stars? So this is not a complicated diagram. Okay, so bear with me for a second. This just represents the structure inside stars. Okay, from the core here to the surface, as a function of mass. Okay, everything that is orange and bubbly is convection, okay, these boiling motion, and everything that is blue is just radiative, okay, where the light is transporting the energy. So if you look on this side, right, you can see over there, see if that thing works, right here, that stars like our sun have radiative core. They're radiative in the deep interior, and they are convective in the envelope. But if you go to very massive stars, the situation is reversed. So the energy is transported by convection in the core and by radiation in the envelope. So they don't have these boiling motion at the surface, near the surface of the stars, which is what generates the magnetic fields in stars like our sun. So we were not expecting at all that these stars should have magnetic field. But the funny thing is that they do. And over the last 5 years, we have learned a lot more about the magnetic field of these stars, the high mass stars, because before we were just not able to measure them very precisely. And I've been involved in a big 5-year program to observe them, with a 5-year program at big telescopes. And what we found out is that the magnetic field of these high mass stars are quite different than the magnetic field of sun-like stars. So first of all, they're very strong. They're very, very strong. We're talking about tens of thousands of Gauss, okay? But they're also very simple. Instead of having like magnetic field in the little sunspots like our sun, it's all over the surface. You have a big global magnetic field of 10 kilogauss, 10,000 Gauss. They're also very stable. They don't show flares. They don't show, dynamo activity. And the funny thing is that it's not all of them. All stars like our sun have dynamo, so they all have magnetic field, but it's only 10%. 1 out of 10 massive stars that actually have a magnetic field. And we think now, from this study, that these magnetic fields are not generated as we speak at the surface of these stars, but they are actually fossil fields that were left over from an earlier phase, even when the star was formed, and the magnetic field just got stuck there in a certain fraction of the stars. And the other thing that I found very interesting about these magnetic massive stars is the fact that there's another difference, another very important characteristic of massive stars, is that they have winds. So our sun have a wind, right? You've heard about the solar wind a little bit, right? So you have these, some material is actually ejected out of the sun, some particles that actually reach the earth. And what did it create? Anybody seen an aurora borealis here? They don't come down here that often, do they? Right? But it's particles that are coming from the sun that get trapped in the Earth's magnetic field and create auroras, mostly at the poles. Okay? But these winds, in my opinion, they're puny. They're not very, they're very, very, very small. They're not very dense compared to the winds of massive stars. The winds of massive stars are 500 orders of magnitude more denser. That's 10 times, 10 times, 10 times, 10 times, 10 times. Okay, these are very, very dense winds. You wouldn't want to live next to a massive star. You would be blown away, literally. Okay? And if you have a magnetic field in there, it makes for quite interesting things. Okay? And I'm going to start for future physics students, hopefully in the room, about my rules of plasmas. So the winds of stars is very hot. So they have different phases of material. You have solid states, liquids, gas, and if you go even hotter, you get plasmas. And plasmas in magnetic field, they don't play along very well with each other. So the plasma is not able to cross magnetic field. Okay? It has to go along the magnetic field lines. So that's the rule number 1. Don't cross the streams. A couple of laughs, okay. The rule number 2 is that you need to listen who's the boss. So they're always fighting with each other. They're like children. It's crazy. So you have the magnetic field, and so on the red corner, you have the magnetic field, which says, I'm staying here. If you want to move, you're not going to need to move along my magnetic field lines. But on the blue corner, the plasma says, the gas, the material says, I want to go there, so you come in with me. Okay? And the gas is trying to stretch away the magnetic field. And they're going to fight each other. Okay? And what happens is quite cool. Okay? So there's going to be that fight between the wind that is trying to get out. It's like, I'm trying to get out of my star. And the magnetic field, which is very big, very large, which says like, no, you're staying with me, you're staying here, which create these big magnetospheres around the stars. So imagine you can see over here, this is the star. Okay, this is about 10 to 20 times larger than our sun. Okay, over here. And you can see the magnetic field. These are magnetic field lines, which extend up to, 1, 2, 3, 4, 5, 6 times the stellar out of the surface of the sun. Okay, and you can see that material is trying to get out, but it can't, and it creates that big disk around the star. And that whole thing is rotating because most of the time the magnetic field is not necessarily aligned with the axis of rotation of the star. So imagine I'm a star, this is my magnetic field, okay, and I'm doing like this. Okay, so as we look, so we cannot see this, so these are not real data, these are not observations, right? There's a mathematical simulation. This is something we do a lot in physics, especially in stars. We cannot really, I wish we could go, that would be the first place I would go, would be that star Sigma Re. But we cannot really, so what we need to do is that we use a computer. We tell the computer, we know the laws of physics. The laws of physics here are the same than the laws of physics where that star is. So let's just mathematically code them. Okay, we can make these codes and just say, see what happens. This is called numerical simulations, and try to reproduce what should happen for these stars. And we can predict what we could see in different wavelengths. Optical, this is ultraviolet, and X-ray emission. Okay, and we can actually, after that, go. Wait a second. We can actually go and take observation. So this is what the model tells us. So we took the magnetic field at the surface of the star. Remember, this is something we can actually measure, right? With that Zeeman effect. We give that to our theoretician friends who do numerical simulations, and they predict what the structure of that gas, what is the fight, who's going to win between the magnetic field and the gas, okay? And basically make a model of what that distribution, that big magnetosphere would look like. And then we can predict what would we see when we take a spectrum of the star, for example. And you can see that as the star rotates, you see the spectrum should change with time. And then this is something we can go and check. Right? And this is what we call the dynamical spectrum. So this is this spectrum over there, okay, which is each line is a spectrum, and this is a time axis. Okay, so it's a way of looking at data over time. And you can see that things are changing with time. And this is what the model, that mathematical structure, predicts. Not so bad, isn't it? That's quite good, I would say. They match pretty well. So we can use observations of these magnetic stars at all wavelengths to try to see if these models are right and to understand the structure of these magnetic fields, the structure of the wind, and how they're going to fight each other. And I'm going to show you, as a last thing, this is my favorite star at the moment. Okay, so its name, I need to find a new name for it. It's like NGC 1624-2. Okay, I don't know when astronomers stopped being romantic, but we went from serious Rigel to HD 378410. Okay, but I call that one -2 just to be cute. And this is that star over there in the middle of that nebula. And it turns out that this is the massive star. It's an O-type star. So these are the hottest of the hottest. Okay, and it has a magnetic field of 20,000 Gauss. It's the biggest, by far, magnetic field we find in one of these very, very massive stars. And we've been looking at it with the Chandra X-ray Observatory recently, one of the NASA flagships. And we've been looking at the X-rays that are emitted in that big magnetosphere, because in this one, the magnetic field is winning the fight, so the gas is not happy and emitting a lot of X-rays. And we're pretty excited as well, because we got these observations and we're trying to figure out what's going on. And we also managed to get Hubble Space Telescope time, who's going to look at our star in the ultraviolet sometime next year. So we're quite excited about that. So we're going to be able to learn more about the magnetic field of these very, very big stars. And I think I'm right on time to take some questions.